Imagine a clock that doesn't need batteries or gears. A clock whose ticking is woven into the very fabric of matter itself, oscillating forever on its own.
And for a long time, that's all it was, an idea, a theoretical curiosity locked away in the quantum realm. But not anymore.
Okay, Arjun, let's start there. This idea is called a time crystal. It sounds like something from a superhero movie. What are we actually talking about?
It's a genuine phase of matter, Maya, but a very strange one. Think of a normal crystal, like salt or a diamond. Its atoms are arranged in a repeating pattern in space.
A lattice structure, right.
Exactly. A time crystal's constituent parts, or more accurately their quantum properties, repeat in a pattern in time. They oscillate at a fixed, intrinsic frequency, continuously.
Wait, continuously? Without any external energy pushing them? That immediately makes me think of a perpetual motion machine, which we know is impossible.
That's the crucial distinction. It is not a perpetual motion machine because it doesn't produce usable energy from nothing. It exists in what physicists call a non-equilibrium steady state. After an initial kick to get it started, it settles into a stable, oscillating rhythm that is its lowest energy state in that configuration.
So it's like a spinning top that, in the weirdness of the quantum world, simply never slows down from friction because there is none?
That's a great analogy. It breaks time translation symmetry. The laws of physics are the same now as they will be in a second, but the crystal itself is different. It's ticking, and that stability, that perfect, repeating rhythm, is what makes it so exciting.
So if it's a phase of matter, how on earth do you make it? You can't just mine it from the ground.
No, you have to create very specific, very extreme conditions. And this is what the team at Aalto University in Finland accomplished in this new experiment, building on their previous work. The results were just published in Nature Communications.
What kind of conditions are we talking about?
We're talking about cooling a sample of a special isotope, helium-3, down to within 1/10,000th of a degree of absolute zero, colder than deep space. At that temperature, it becomes a superfluid, a liquid with zero viscosity.
Okay, so you have this incredibly cold, frictionless fluid. Where does the crystal part come in?
Inside this superfluid helium, they use magnetic fields to excite quasi-particles called magnons. You can think of a magnon as a tiny collective wave of magnetic spin, like the wave spectators make in a stadium.
So it's not a single atom moving, but a wave of energy passing through the system.
Precisely. And they were able to create a dense cloud of these magnons, so dense that they formed something called a Bose-Einstein condensate. It's another exotic state of matter where all the quasi-particles start acting in unison as a single quantum object.
Wow, and that unified object is the time crystal.
Yes. This condensate of magnons began oscillating spontaneously between two different quantum states, back and forth, with a stable, predictable frequency. They had created a continuous time crystal.
That in itself is just mind-blowing, but that wasn't the biggest news here. They created this incredible isolated thing, but the breakthrough is that they finally touched it, right? They connected it to our macroscopic world.
That is the heart of it. This is the work of a team led by Professor Pertti Hakkinen, with Jerry Mäkinen as the lead author. For the first time, they coupled a time crystal to an external physical device.
How? What kind of device can talk to something so fragile and so bizarre?
Something surprisingly simple, in concept at least, a mechanical resonator. In this case, it was an incredibly tiny vibrating wire, also inside the supercooled environment. Think of it like a miniature guitar string.
And the time crystal is in the same room, so to speak? Did they just hope they would interact?
It was much more deliberate. The oscillating magnetic field of the magnon time crystal exerts a tiny force. The team designed the system so this force would push and pull on the vibrating wire.
So the time crystal is plucking the guitar string.
A perfect way to put it. And what they observed was extraordinary. The wire, the resonator, began to vibrate. More than that, its vibration synchronized perfectly with the time crystal. They were oscillating at the exact same frequency, at around 1,000 hertz.
They were talking to each other. The time crystal's rhythm was being imprinted onto a physical object.
A handshake between the quantum and the classical worlds. The time crystal's internal, untouchable oscillation was now expressed as the physical movement of a wire, a movement they could measure precisely.
This feels huge, because observing a quantum system is notoriously difficult, right? The very act of looking at it can change it or even destroy it.
Exactly right, and that's why this is more than just a cool demonstration. This setup provides a non-invasive way to read the state of the time crystal. Instead of poking the fragile magnon condensate directly, you can just listen to the wire it's talking to.
So the wire becomes a translator, a sort of Rosetta Stone.
The paper describes it as a cavity optomechanics-like platform. That's a bit of a mouthful, but the concept is beautiful. In optomechanics, you have light in a mirrored cavity, and its pressure can move a tiny mechanical object. By observing the light that leaks out, you learn about the object's movement.
Okay, so what's the analogy here?
Here, the time crystal acts as the cavity. Its state influences the mechanical part, which is the wire. By measuring the wire's vibration, we are effectively reading out the state of the time crystal without ever touching it directly. It's a clean, continuous signal.
It's a readout mechanism. You've taken this theoretical curiosity and given it an I/O port. You've given it a way to interface with technology.
That is the leap. It moves time crystals from the realm of fundamental physics observation into the world of applied quantum engineering. It's the first step to actually using them.
Which, of course, brings us to the big question. What for? The headline that always comes up is quantum computers.
And for good reason. One of the biggest challenges in quantum computing is something called decoherence. Qubits, the basic units of quantum information, are incredibly fragile. Any interaction with the outside world, heat, vibration, can corrupt their state.
They lose their quantum nature.
Yes, but a time crystal, by its very nature, is a robust, self-correcting, periodic system. Its oscillation is protected by the underlying physics. It's intrinsically stable.
So you could use that stability. How?
There are a few possibilities. This specific type of time crystal is what's known as a continuous one, which makes it especially useful. It could act as an incredibly precise clock or metronome for a quantum processor, ensuring all the operations happen in perfect rhythm. Or you could encode information in the phase of the time crystal's oscillation. Its state could itself be a qubit, and potentially a far more robust one than we have today.
So this isn't a quantum computer in a box, but it might be a blueprint for a critical component we didn't even know was possible.
That's the right way to think about it. It's a new building block. The researchers at Aalto even note that time crystals could function as sensors of unprecedented sensitivity because any tiny disturbance would slightly alter their very stable frequency, which we can now measure. It feels like discovering a new element on the periodic table, but for states of matter. We don't know all the ways we'll use it, but we know it's fundamental.
We've opened a door to a room we didn't know existed, and now we've taken the first step inside. It's a profound moment.
For the first time, a time crystal is not just an it, but a vow, something we can have a conversation with.
A conversation that might just help build the future.
I'm Maya.
And I'm Arjun.
See you tomorrow.